All right, so we'll get started. So welcome everyone to the SNAPP seminar. Today we are very happy to have Sasha Stolyar from UIUC giving us a talk. So for this audience, Sasha probably doesn't need too much introduction, so I'll keep it brief. So since 2017, Sasha has been a professor in the ISC department and then coordinated science lab at University of Illinois, Urbana-Champaign. His research interests are in stochastic processes, queuing theory, and stochastic modeling of information, communication, service, and supply chain systems. He's an Informs Fellow and then received the Informs Applied Probability Society 2004 Best Publication Award and the Sigmatrix 1996 Best Paper Award. And today he's going to talk about non-work-conserving load distribution systems. Sasha, the floor is yours.
Okay, thank you, Johan, for the introduction, and thanks everybody. So the subject is non-work-conserving load distribution systems, and I will jump right in. So this is the specific system which we are going to look at. And by the way, I know that the rules say that mostly people do not ask questions, during the talk, but it's okay it's okay to interrupt. Please do that if necessary. Okay, so this is specific. Let's look specifically at this system, right? So this is a system with large number of servers, and so these things represent servers, and these bars represent the amount of workload the server has, right? Currently, so workload is unfinished work of the server, right? If you let it work, this is the time required to drain the entire work. Okay, so this system receives the flow of jobs, and jobs can be of multiple classes, right? So for example, the class J job, right? It has multiple components, right? So suppose this class has 3 components, parameter dj. These are the sizes of the components, right? So this is potential amount of work that I will add to the servers. When the job arrives, it chooses it selects random set of servers, dj servers uniformly at random. So here it will be these 3. Right? These components are placed on servers like this one, and this one. And the system has a feature which is called cancel on completion redundancy, which means that as long as 2 of the there is a parameter kj, as long as, for example, 2 of the components finish servers, which will happen in this picture, it will happen at this point in time, the remaining service of whatever components left, it will be canceled, right? So it will not happen. So the component sizes are potential amounts of works which a job adds, right? But the actual amounts of work which are added are not just component sizes. So here is equal to the component size, here is equal to the component size, here only this will be added, right? And not this. Okay. So this is type of the systems we are going to look at, and the motivation, the standard motivation is that the job represents user who tries to retrieve its data from some server farm, right? And the data is located on some subset of servers, for example, 3, right? And you get the information you want if you completely retrieve 2 out of 3 chunks of data which you have somewhere, right? And the random selection set of a job, it represents the fact that different jobs have their data located in different places. There are other motivations, but this is this is one of the primary ones. Okay. And in general, we want to view the system a bit more generally, as we will see later. Okay. So this is formally in word description of what I said. So there are n servers which will become large. They process work at unit rate. There are multiple job classes. Each class J jobs arrive as post-on process. The rate of arrival is So this is lambda n times n is the total rate of arrivals of all jobs, right? So this is lambda n is the arrival rate per server, and the probability, pi n j, this is the job of class j. So of course, this sum up to 1. Dj is the number of components, right? Kj is the number of components which needs completion. About the component sizes, we make an assumption that they just follow some exchangeable distribution. Okay, so IID is good enough, right? So there's a symmetry. For some results, for main results, we will actually need the assumption that the component sizes have finite second moment, but it's not for all results. But let's assume that this is throughout this talk this is true. There are some non-restrictive technical assumptions about this distribution. Let's not talk about it. They always hold. Okay, so cancel on completion is the main feature which I just described, and this makes system non-work-conserving in the sense that you describe on the next slide. Our primary interest will be asymptotic regime when n goes to infinity. The rate per server goes to something, and the probabilities of different classes also go to some distribution. And the main question we want to address is, when do you have a steady state asymptotic independence of server workloads? Okay, so steady state asymptotic independence is a very long phrase. So, in this talk, I will call it Anzacs, following Maury, Bramson, and others. So instead of saying steady state asymptotic independence, I will say Anzacs. Okay. Okay, non-work conservation, why we call it non-work conserving. Okay, so work conservation can be understood in the following way, right? So when the job arrives, right, so it brings some new actual work to the system, right? Whatever is canceled doesn't count, right? It brings some random amount of work into the system, and work conservation can be understood as, the job arrives, you get a realization of total amount of work, right? Then it's somehow placed on servers, but this random total amount of work is independent of the state of the system. Okay, this is one way to understand this. Okay, you can understand work conservation more weakly as expected total amount of new work does not depend on the system state, right? So the system which we are looking at, specifically this cancel completion redundancy, it's non-work conserving, even if work conservation is understood in a big sense, right? So if you go back to this picture, you will see that typically even expected amount of new workload which will be added, which is this plus this plus this, it will depend on the state of the system. Specifically, it will depend on the workloads on the servers which you select, and even more specifically, it will depend on the relative workloads of the servers and the differences, right? Okay, so this is non-work conservation. So again, we're looking at to have it specific. We're looking at cancel completion redundancy. But I want to, I want you to keep in mind that vast majority of analysis which follows, it's not limited to this system. It's what will be important for our analysis here is that this system has two fundamental properties. One is monotonicity, which means that the usual thing. If you have two systems, and one starts with the largest state, you can couple them, so it will always have a larger state. Okay. And the second property is, egalitarian trend. You can call it load balancing. It basically means that on average, servers with lower workload will tend to receive more new workload, right? So there's a trend towards keeping workloads closer together. Okay. So you will see that we are not using much of anything else. So previous work. So to tell the truth, I'm not aware of previous work on proving Anzacs for non-work conserving systems. multi-component systems, right? So there are some proofs of ansatz for work-conserving multi-component systems, with egalitarian trend. One of these papers is Bramson and others, where they prove ansatz for least load D discipline. That's the power of D choices when you have the job arrives and the entire workload goes to the least loaded server. Okay, so I should of course mention that this is a small fraction of what's done in this paper, but regarding this particular question, that's what's done there. And there is a paper which Sevashnier and I did a little earlier. So it proves ansatz for a fairly large class of disciplines, which includes so-called least load and water filling job classes. So this this includes this as a special case. But important thing about this paper is that it's the systems of work-conserving. And you can do it for other work-conserving systems too, more than in this paper, but work conservation is crucially used there, as we will discuss a little later. Okay. So the proofs there are not that many, but the conjecture, this ansatz conjecture, is very fruitful, and it's very frequently used in in the literature. So I just put two papers. There is more. So this is the paper which actually obtains explicit expressions for the waiting time of a job, which means the time time until everything is completed and until the job is done. So there is no proof of ansatz, but assuming this is true, you get explicit expression. So this model is within the framework of today's work we're going talking about today, but it's also in the framework of this paper because it's work conserving. Right. There is also, I like to refer to this as a very nice paper. It has a very large variety of systems. It's well beyond of the class that we are looking here, but some of them are non-work conserving. And again, one of the points of this paper is that they try to find some expressions of the waiting times, for example, assuming ansatz holds, right? So some of the models, not all, but some of the models in that paper are within our framework. So we formally prove the conjecture which is there. So as we will see later, this ansatz conjecture, right? Using it means finding fixed point of the mean field limit, which we will, in the terminology which we will have later. It's very useful, particularly when you analyze. It's very useful to look at the system, from the point of view of moving particles, right? So if you can represent servers as particles, right? Server workload will become location of the particle. So this particle locations on the positive half axis, right? And the particles move like this. So when nothing, normally they move left at speed 1, each of them, right? And from time to time there is a urge, in the system for particles to jump forward. And when this urge happens, it can be of different types, of different classes J, right? Then you select subset of particles, and then these particles somehow jump forward. Okay. So in this picture, like these two particles jump, and this particle doesn't jump. Okay. Or it may be that this particle jumps here, and this particle jumps here. So this is cancel on completion happens here, right? And there's a left regulation. There is a left regulation boundary. So if any particle hits 0, it stays at 0 until it maybe jumps forward. Okay.
Yeah, Sasha, a quick clarification question about the model. So you say that a class J job comes in and then selects DJ servers.
Right.
These servers, are they specified up front, or are they like random?
No, uniform rate
subset?
random. I think I mentioned that. I should have emphasized.
Okay.
Yeah, that's it's symmetric system. Yes. Yeah. Thank you.
Okay, so I see. So only difference is the DJs, the value of DJs, they're different between
Yeah, and the distribution of component sizes. You know,
right.
there is
Okay.
distribution of component size. Okay.
Okay. All right. Thanks.
Yeah, thank you. Okay, so as you already guessed probably, so since we are letting n go to infinity, we will look at the mean field representation of the process. So, you know, as usual, you know, the state of the system at time t can be represented by, you know, by this function, which basically tells you, you know, fraction of the particles which are located to the right of point, you know, w, right? So this is the system state. So it's like an empirical, you know, that's the actual distribution of particles, right, at time t, right? That's all it is. So except, you know, this is a complementary distribution function, right? So obviously this xn is a Markov process, and if process has a stationary regime, stationary distribution, we will use this notation for this. So this is a random state of the process in steady state if steady state exists. So this infinity, you know, indicates you know, time at infinity. Okay. So the first question you have to, you know, you have to address is when this system is stable. And you know, this is the first time when we, you know, get a little bit of difficulty with non-work conservation. What does it mean that system is subcritically loaded? Okay, so you don't know, you know, average amount of work which job brings, right? So, you know, if we denote by, you know, lambda n bar, right? So this is the upper bound of those values of lambda of arrival rates per server, you know, under which the system is stable, right? So it is something, you know, by monotonicity, you know, there is some well-defined upper bound. If we denote by rho n, right, the system load, you know, in steady state. So this is probability that the server is busy, assuming the system is stable, right? Then the most natural qualitative property which you expect from the system is stability, you know, for the full range of loads, which basically means that, you if you pick different lambdas, so for this lambda, you know, your load is this. If you pick, you know, different lambda, your load is something. And the most natural property that you would expect is that when your lambda actually approaches this this upper bound, the steady state load approaches 1. Okay, this property is not automatic, but, you know, it's a bit of a difficulty, but it's not a serial difficulty. You can show that for the system we are looking at, it in fact holds, right? So it's not possible that, you know, as you approach this boundary, your load, you know, converges to something, you know, like a 70%, and then there's a phase transition and there's a jump to 1. So this cannot happen. So I will discuss a little later why this is not, you know, it's a little bit of difficulty, but it's not a serious difficulty. In fact, you can characterize this upper bound fairly easily under mild assumptions. Okay, so there is something else that we can do for the finite n system, and something which we will, you know, very substantially use later in the asymptotic analysis, is the tightness of the centered distribution. Okay, so remember x is the distribution of particles, right? So x bar, suppose it's the average of the allocation, okay, center of gravity, right? And suppose circle x is the distribution of particles, you know, centered at the mean, at the center of gravity. And we will use this notation flx. This is the lth absolute moment of the distribution with respect to the mean of the center distribution. So that's all. Okay. So you have a bunch of particles. You know, there's a mean somewhere, right? And you take a lth moment with respect of particle locations with respect to, you know, to the average. Okay. So this is just a reminder. For the analysis here, it's really useful to have the view of the system as a particle system. Okay. So what can we do for the finite n is, we can show that the first absolute moment of the centered distributions is uniformly upper bounded. Okay. Again, there's some work involved, but it's not terribly terribly difficult. You can use f2 second moment as a Lyapunov function, so you can show that the drift argument. You can show that the first moment would have to be uniformly bounded. So what we need it for, and what we will need it for, is that if, for example, you look at quantile nu, I know, like a 90th percentile of the distribution, like a uniformly in n with high probability, like a 90th percentile of the distribution, it cannot be, it's within some constant of the mean. Okay, so in words, this tightness property, it means that the particles, regardless of load or regardless of anything, these particles stay close together. Right. So formally, the distribution in the space of those empirical distributions is tight. Right. This is very useful. We will see later. So you can also look. So this is the system. This is our actual system, right? It has the regulation boundary on the left. If you look at this system, without the boundary, you will remove it, right? So you look at the free particle system, right? This particle system, nothing prevents it to going anywhere on the left or on the right, right? So if you introduce a little bit of additional assumption, also very non-restrictive, this particle system, if you look at the centered systems, it will have a stationary distribution, and this stationary distribution will determine, the average drift of the whole thing, right? It can be positive or negative. So if you define, for example, gamma n as the average displacement, average jump forward of the particles given one urge, to jump, right? Then this is determined by the stationary distribution of the centered states. So this is a well-defined thing. It may not be defined explicitly, but it is something. It's in terms of stationary distribution. Then it's not very hard to see that upper stability bound is 1 over this, right? So it's basically the stability condition of original system is lambda n gamma n minus 1 has to be less than 0, right? So this is the drift. This is the drift of the particles if they would not be moving left, and this is this is the drift due to their movement to the left. Okay, sorry. Okay, so back to what we actually want, right? So our main goal is Anzacs, right? So its formal definition is as follows. So we have this property Anzacs hold for a given value of lambda. If there exists some proper element, x star, right? With load less than 1, and it's proper in the sense that this state, this function is such that you go to 0. So this will be our typical picture. This is x star, such that as n goes to infinity, your steady states you will concentrate at this fixed at this point. Okay. If this happens, as a corollary, then in steady state, the workloads of any finite set of servers will be asymptotically dependent. So it's equivalent thing, saying that you have this property in the mean field, for the mean field limit is the same as saying that you will have asymptotic independence. Okay, so the question, one of the questions so for which values of lambda you have ansatz. Okay. So the difficulty is, again, what does it mean that you have a subcritical load? The usual statements for work-conserving systems, right? So if you have a system which is subcritically loaded, right? So in the limit your load is less than 1, then you have ansatz. Okay. Here we don't know in advance what the load is. Okay. There is one condition which is sufficient for the ansatz to hold, and let's call it we'll call it inherent subcriticality. And it's like this. So suppose for each class J, there is some number Sj bar, which is somehow upper bound on the expected amount of work which this job will bring, regardless of the state of the system, right? So no matter what set you select, no matter what workloads are on that set, the average amount of work will be upper bounded by this. Okay. Then system is inherently subcritically loaded if we have this if we have this thing, right? So we assume worst case, where somehow we know the worst case, system is inherently subcritically loaded. Okay. So if system is inherently subcritically loaded, then yes, ansatz holds. This is true. But this is kind of, this is less interesting question. So, the real question is, what if you don't have inherent subcriticality, right? So what do we do? Okay, so the most natural, the most benign situation which you can imagine is that you have ansatz for the full range of loads, which means the following, right? So there is some upper bound lambda bar, right? Such that for any lambda up to that boundary, right? You have ansatz with some proper element lambda star, which depends on lambda. And the most benign situation is when, as your lambda is approaching this boundary lambda bar, your load will actually approach 1. Okay, we will call it ansatz for the full range of loads. Okay, this is the most natural thing you would expect. Okay, so this is not automatic. Who said that? Who said that? Definitely there is some upper bound lambda bar that is not hard. Who knows that if you look at this limiting load, so suppose ansatz holds here, ansatz holds here. Who knows that the corresponding load will not converge to something? So remember, we had a similar thing for the just for the stability, but there this question was resolvable fairly easily. Here, I mean, it's not obvious. Okay. So what do we do? What do we do about it? So consider first work-conserving case to see the difficulty, right? The work-conserving case which we'll consider is a special case when your component sizes are IID exponential. Okay. It just happens if you look at the cancel on completion redundancy, right? Like we are discussing, right? And your component sizes IID exponential. It just happens that the total amount of workload which is brought in, it actually does not depend on the system state. The system happens to be work-conserving. Okay, so this is explanation. So if you have 3 components and they have exponential IID exponential sizes, then the total amount of workload, which is like here plus here, until you have the first completion, right, will be exponential, with the same mean as component size. And then if you look at the amount of work, additional amount of work brought until the second completion, this also will be exponential. It will be independent of the first thing. Okay, it just happens. We can check that. Okay, that's actually observed in the previous paper with Sevashner. Right. So this is a work-conserving system. So you know that total amount of workload brought by class J is this no matter what. Okay, work concern. Okay, we are looking at the mean field limit of the system. So, right, so n goes to infinity. So naturally, we're looking at like a transient behavior of the process. Right, the tool to get asymptotic oscillation distribution is to look at the transient behavior. So xt is the limit of the transient behavior of the system as n goes to infinity. So this process, which in this case happens to be a well-defined deterministic process, is we call mean field limit process. So it's like this, so you have this function. This is your state at time t, and somehow it involves in time. Okay. So again, for work conserving, we're looking at work conserving system, right? So there is a well-defined limiting load of this system, right? We know the workload for each class J. We know the probabilities. This is limiting load. So if you're looking, for this system, if you're looking at the mean field limit, which starts from the empty state. Empty state means no work anywhere, right? So the function is just like this. If you're looking at the mean field limit, which starts from the empty state, it will increase somehow, right? It will, by monotonicity, it will increase somehow. It will have to converge to something. That's something we can call x star, and it will be fixed point of the mean field limit. So if you start from here, you will stay in it. Okay. And again, it's not hard to see that this x star will be proper. So it's not possible that you do not converge to zero, that you converge to some some positive epsilon. Okay. And it's also not hard to see that the load to this x0 star, right? It cannot be larger than this nominal load rho by work conservation. Okay. If it would be larger, then you get a contradiction. Right, it means that you start processing more work than it arrives into the system. Cannot have. So this is easy. So in fact, it's also it's possible to show that in fact this x0 it has to be rho. Exactly the nominal load. And the way you do it is, you're saying, in addition to my original system, I will look at a truncated system. Truncated system at level C, like here shown, right, is very simple. So it just like original system, only any workload which goes above level C is clipped and thrown away. Okay. So what you can show that for any truncation level, there will be some well-defined fixed point of the system, right? And now we call it this. And when C is large enough, you can see that this thing has to be close to our fixed point, by work conservation, because if C is large enough, right, you can show that the amount of work which will be lost due to clipping at this level is small. Okay. Right. So this is close to rho, right? And this level C can be chosen far enough, so this is arbitrarily close to rho. And our system dominates, clipped system by monotonicity, so it has to be. Okay. So we very essentially use work conservation to show that in fact this fixed point will have load exactly rho. Okay. So this x star is in fact the unique fixed point of the system, and then we can get Anzacs. Then we can get Anzacs by saying, okay, now we will look. So this station distributions of system for each n, right? If you look at any weak limit along a subsequence, any limit must be concentrated on the trajectories which are above this fixed point. and it cannot be strictly above with positive probability, because if it happens, then with non-zero probability, your load will be larger than rho. It's a contradiction with work conservation, and you're supposed to have ansatz. So any limit of sequence of stationary distributions will have to sit at this fixed point. Okay. So now we are going back to our non-work-conserving system, and but I'm supposed to stop for a minute or two in the middle, just in case there are questions. Please go ahead.
Hey, Sasha. I was curious. I would have thought with the cancel on completion, it would have caused a jump down. I think I'm missing something in your model.
Sorry, Rose, can you repeat? It would be what?
It would cause a jump down when you have canceling.
Okay.
What is that not model? I'm missing something, I think.
Okay. No. It's just a matter of definitions. So our view of the system is that jump forward, it only includes the actual work which will be added. So if something jump forward is not the actual component size, it's just what actually happened. Okay.
I see. Okay, so you do a back the envelope calculation or something to figure that out. I see. Okay, thank you.
Okay. All right,
Sasha, I think
okay.
I think Rami had a question in the chat. Is it known what dynamic equation xt satisfies?
Yeah, it's coming. Yeah. Yes. Okay. It will not be. Let me talk about it a little later. Okay.
I also have a clarification question.
Sure.
Also, you start with this empty states x empty set. Do I want to? But x is the fraction of servers with work greater or equal to to w, right? So is it actually starting at 1 uniformly, or is it starting at 0?
No, it's at 0. So this is greater. If this function x is such that it's identical 0, right? It means that the fraction of servers with workload greater than any epsilon is 0.
Okay. All right. Yeah.
It's just sorry. It's just up to 1 minus. Yeah.
Okay. Yeah. Okay. Thank you.
All right. So let's move on. So back to our regular programming. Back to non-work-conserving systems. Okay. So let's try to prove ansatz for the full range of loads. Okay. So what we need to, by the definition of this property is that, this load of the point at which everything is concentrated, right? It goes to 1 as lambda increases to this upper bound. Okay. But again, we don't know what rho of lambda is a priori because of non-work conservation. Okay. So to approach this, let us construct, instead of trying to construct this function, let's construct, inverse function. And that's what we will do. So suppose we will fix some load rho less than 1, any rho less than 1. If we can construct lambda such that when lambda n goes to lambda, your sequence of stationary distributions concentrates at that point, concentrates at some point with load rho, right? Then we are done. So if we can construct this inverse function, we are done. Okay. So let's start moving in this direction. So for each n, we will pick lambda n such that the actual system load is exactly rho. So that we can do by stability for the full range of load. So remember that was a stability result. We can do that, right? For any rho, we can choose lambda so that system load will be exactly rho. Okay. Then consider any subsequence along which those lambda n's converge to something, and let's try to prove that if for this particular lambda, yes, you get you concentrate at a point with load rho which we a priori chose. Okay. So let's try to prove that. Okay, so this is the key difficulty posed by non-conservation in all this business, at least from my point of view. So let's start. Let's try to proceed just like in work-conserving case, right? So we start with the empty system. We look at the mean field limit, which starts at in empty state, right? Fine. By monotonicity, it will have to increase. It will have to converge to something. That's something we will call X star. Okay. The actual load row which we fixed. Remember that's part of our construction. It may be larger. We don't know that this is exactly equal. Okay. So who knows that limit of stationary distributions will not be would not be concentrated on some trajectories which are above this X star, which is in fact the minimum fixed point, right? So we start from empty and we converge to it. It has to be dominated by any other fixed point. Who knows that the limiting process will not live on trajectories which dominate this. Okay, this is the key thing. Okay, so now to partially answer Rami's question, you can write equation for any fixed point satisfies this functional differential equation, which means that if this is your fixed point, like this one, right? So if you're looking at this point, the derivative has to be equal to lambda times some function of the entire shape here, and it's nothing fancy. Basically this is the rate at which particles, this derivative, right? It's the rate at which particles cross this point W from right to left, and if it's a fixed point, it has to be equal to the rate at which they jump over this point from left to right. Okay, so this is average number of particles which will cross point W if a job arrives into the system, right? A job can choose some servers, right? And some of the particles will jump over and some will not. So this is the average number of those which will jump. Okay, so fixed point satisfies this equation, but yes, this equation holds just for X of t. To answer Rami's question, yes, it's not just for fixed point. If you have X of t, right, there is a well-defined there is a well-defined rate at which you jump over to the right. There is a well-defined rate at which you cross to the left, and the difference will give you derivative at a point. Yeah, you can write equation. The short answer is yes, you can write this equation. Right, differential equation for X of t, for the evolution of X of t. But we will be interested only in equation for fixed point. Okay. So converse is also true. Okay, so any solution to this equation will be fixed point if we understand fixed point a little bit more generally, right? Which means the following, right? So you can, I can pick initial condition, right? So for example, this one, right? And I write solution to this equation. Nothing will, you can show nothing, nothing can go wrong. There's a unique solution, depends uniquely on the initial point. Everything is fine, right? So suppose you may have a solution which gives you proper element, right? So you have a convergence to zero. You may have another situation when you solve this equation and the solution will hit x-axis, right? In this case, what you get, in fact, fixed point over truncated system. Okay, it may happen that if you start at some point, you get a solution which converges to some to some epsilon, positive epsilon, not to zero, right? This is also not such a big deal. The interpretation of such not proper solution is this is fixed point for a system where there is some fraction of servers have infinite workloads always, right? So no matter what, they they have infinite workload at the beginning and it stays infinite, right? So whatever is added, it's still infinite, right? So these improper fixed points, improper solutions, they have a very clear interpretation. In fact, the infinite element is also fixed point. So infinite element is identical one, means everybody is busy. Everybody has infinite workload, and then it never changes. Right? This is trivially fixed point. We will call it x double star. Okay. Key result. The key result in the whole business. So you have Anzacs for the full range of loads. If you have uniqueness of the fixed point, so I will do a shortcut a little bit. So the unique condition is like this: for any parameter lambda, right? For any lambda, right? And any epsilon, right? And any epsilon, right? You cannot have two fixed points, which both converge to, to the same level epsilon. Okay, so it's not just that there's a unique fixed point which is proper. Okay, you need a little bit more. Right? You cannot, for any epsilon, you cannot have two solutions which converge to the same level. Okay, if this is true, under this uniqueness condition, then yeah, you have Anzacs for the full range of loads. And hopefully I will show a little bit later that this condition is not vacuous. Okay, let me go very quickly. So this is a proof. All the proofs are just pictures, so don't worry too much. So the first stage, the first step, of the proof. So as usual, so suppose this is some subsequential limit of station distributions, right? So the first step is to show that this limit is concentrated either on proper elements, which converge to zero, or on the infinite element. Okay, so this is not possible. It's not possible to have proper elements, with probability 1, which converge to some epsilon. Okay, roughly this is true because if this would be happening with non-zero probability, you would not have a tightness of particles, right? So we have this property that the particles are supposed to stay together. This will be violated because, for example, I don't know, like with non-zero probability, your 20th percentile will be here, and your 90th percentile will be somewhere far away. It cannot happen, right? So this is the first step. Second step is, any proper element with probability 1, in fact, has to be equal to this, equal to the fixed point x star, which is the minimum fixed point. Okay. This is very key. This is very key. So the argument goes like this. I will do it very quickly, right? So, this is our minimum fixed point. By uniqueness, if we change initial condition of station distribution a little bit, we will move it up. We will get a trajectory which will not converge to zero. It will converge to some small epsilon. It will be closely approximating minimum fixed point, but it will right? It will stay away from x-axis. Okay, so this is this blue one. Right. What you can do if you look at a shifted version of this blue fixed point, if I shift it right, suppose far enough, right? Let's call it shifted fixed point. Okay. The thing is, if you make this shifted fixed point your initial condition, it will have to converge down to this blue fixed point, right? The reason is like this. So if this is shifted fixed point, right? If I will move my regulation boundary to this point, right? I didn't change anything. It's still fixed point. And then I will just release it. I will let it go. Right? So this whole thing will have to be monotone decreasing. It would have to converge to something. And that something cannot be anything different from this, because that would violate uniqueness of the fixed point. So this gives us basically attraction to this. So what we can show that if you take any improper, if you take any proper fixed point as green one, right? It can be something, but it converges to zero, it's proper, right? I can always dominate it by a shifted fixed point, which is non-proper, which is, a little bit converges to something which is, a little greater than zero, right? I can dominate it, and I can start the process from this state. It will converge to the blue one, which closely approximates minimum fixed point, right? And so you have this dominance. So any non-proper initial state, if I start from it, it will converge down to the minimum fixed point. Okay, this is the most important thing. And the third stage, the third step is, we still have a problem. So now we know that distribution is either on the minimum fixed point or on the infinite one. Okay. So in the third stage, we show that this cannot happen. Again, we're using tightness. Basically now I will not go through details of this picture. Now, basically, what happens? What does it mean that with non-zero probability, in the limit you are on the infinite fixed point? It means that with non-zero probability, all your particles for the large enough n, almost all your particles are, far away to the right. Okay, and then what can you do is you can show that. Okay, if you pick for example like a 90th percentile of distribution, you basically can use this this majorization argument, right, to show that, like for example, 90th percentile over the finite interval, it would have to move left on average, and you can do all the details. So again, we're using tightness to get a contradiction, to show that, if this would happen with non-zero probability, right? Like for example, your 90th percentile would have a negative steady state drift, which is not possible in steady state. What is important? What is important is that, anything I said so far, you can, if you think about it, we did not use the structure of cancel completion redundancy much, right? So we only use those two properties, right? So the egalitarian trend, so the particles tend to stay together, and monotonicity, we hardly use anything else. Okay, so this key result, it's fairly generic. It has very little to do with cancel completion. Okay. Now, maybe this condition is vacuous. Okay, it's not vacuous. Okay, now let's talk about use it for cancel completion redundancy, right? So this condition holds on the cancel completion redundancy if you have, this kind of monotonicity, call it demonotonicity. So suppose this is the workloads of the selection set, right? We will order them. Okay. So D will be the vector of differences, right? So this is the distance from W1 to W2 and so on, right? So this is from WD to D-1 to WD, right? And suppose this is, expected amount of workload that will be added if you have this kind of differences between workloads, okay? If this function is monotone non-increasing in D, right? Then you have FP uniqueness. So basically, if you spread out workloads of the selection set more, on average you get less workload. And basically, this is the proof. We can show that if you have, for example, two fixed points, right? And uniqueness will not hold. So for example, they are both proper, they converge to zero, right? You can show that if you look at the difference of inverses, if you go down here and you look at the difference of inverses, it would have to be increasing, right, as you go down, right? And then you get a contradiction. So for this fixed point, workloads of servers, they are more spread out, okay? So on average, the amount of workload added has to be less than for this one. And yet, the load is larger contradiction. Okay. still, it's something not very tangible. Here is very tangible. So this demonotonicity, it does converge in the special case when your components are IID with increasing hazard rate. Okay, so exponential has constant hazard rate, increasing hazard rate. Uniform distribution has increasing hazard rate. Deterministic distribution has it's like a degenerate increasing hazard rate, which is first 0 and then infinity. Right? It can be a mixture of those two. Okay, so here's the simple reason. Special case. Suppose you have equal components, right? Deterministic component size is a special case of increasing hazard rate. So trivially, in this case, right? So suppose these are your workloads on the selection set. So you have these 3 components of exactly equal size. So obviously, if these initial workloads, you will spread out a little more, right? So this one you move here, and this one you move, even more. Clearly, that more will be canceled. So here, this will be canceled, and here this will be canceled. So in this case, for deterministic, it's rather obvious, but this is true for any increasing hazard rate. Okay, just sorry, one minute. I'm almost over time. So in fact, that case of inherent subcriticality, it's actually an afterthought of this analysis involving uniqueness of fixed points. It's also proved, basically this way. So if you have an inherently subcritical case, you can show that you have fixed point uniqueness like a locally for the lambdas. Okay, maybe not all, but locally it is. And another thing is, if you have increasing hazard rate components, you can very easily get non-trivial upper bound on the total amount of work, which can be used to use this inherent subcriticality. And by the way, if you have IID decreasing hazard rate components, right, then the opposite is true. So the more you spread out workloads of the selection set, the less average workload you get. You can show that. Okay. So in this case, in this case, you also get a non-trivial upper bound on the average amount of work. It's basically it's kj average size of one component, right? Because the best case in terms of minimizing added workload is to spread out workloads as far as possible, and then the k components will be served completely, and the remaining d minus k will not be served at all. Okay? And the final slide is, from the general point of view, what we are looking is the behavior of this kind of sets of particles, right, which have which have this these two properties, right, egalitarian trend and monotonicity, right, and we're looking at the mean field limits, and there is lots of interesting questions like for both regulated systems and unregulated systems, and especially non-work-conserving cases, because, for example, if you have a free system and it's non-work-conserving, right, you don't know in advance what is the drift of the whole thing, right? And these kind of systems, both free and regulated, they have applications, right? So I have another paper about another line of work which looks at these kind of systems and trying to determine. But what I did so far here is work conserving. But anyway, this kind of particle systems are of interest, I think. And now I'm formally over time. So if you're interested in more details, there's a paper. Thank you.
All right. Thanks,
Sorry.
Sasha, for interesting talk. Yeah, no worries. You're right on time. Do we have any? We're a little short on time, so do you have like a quick question or two?
I have a brief question.
Sure.
So I think for this work, the assumption is that the number of servers seen by a job does not change with n, but I've
Correct.
seen some redundancy or fork join models where it does.
Right.
Does this technique extend at all to that setting?
No, I don't know, but it will definitely will be cumbersome. But I know the work that which you mean is by Weiner, Bank, and others, right? Yeah. So that that system does not have egalitarian trend. So you may have a difficulty showing that particles stay together, right? But it's definitely work conserving. But it's a different kind of works, right? If selection set is increasing, maybe you can do similar things, but it would be more involved.
Okay, thanks.
But that system is definitely work conserving, and it does not have egalitarian trend, right? Because how much workload server receives does not depend on anything at all.
Of course. Yeah. So I guess I was wondering, if we took this system, but we replaced the selection set by log n servers or something,
right,
then we'd have egalitarian trend, but we wouldn't be work conserving.
Right.
It seems interesting.
Yeah.
Yeah. Thanks.
I have a question.
Sure.
Yes. So you say that work conserving is redundancy with IID copies, and for example, redundancy with correlated copies or identical copies could be non-work conserving, right?
Well, yeah, correlated. Yeah, I mean, in general, it's this system cancel completion is non-work conserving. It just happens when it's not just IID, when it's IID exponential. It happens.
Okay.
It happens to be work conserving.
Okay.
So it's work conserving in a strong sense. So the distribution of the amount of work does not depend on the system state.
Yes.
Okay. In the interest of time, I guess we'll formally stop here. We'll just hang about for a few minutes in case people want to hang around for a few more questions. Let's thank Sasha again for a great talk.
Thank you.
Yeah. So Sasha, if you're time constrained, we can.
No, I have to. I will have to go at quarter to the. I have 12 minutes. I have 12 minutes.
I see. I have a quick question. So some of these works on redundancy systems, I think they have these kind of server dependent rates. So here, all the servers, and so it's a very nice particle system representation because all the servers have a service rate of 1. Is it an easy extension to the case with, let's say, servers having server dependent rates?
I mean, yes.
No, I don't know. Yeah.
No, I wouldn't say. No, I wouldn't say it's easy extension, but yeah, it will be different model. Suppose you have, have servers are fast, rate 1, and have servers are slow, rate 1/2, right? Yeah. So your particle system, it's subdivided into 2 parts, right?
Okay.
Like a subset. Yeah. The free system then doesn't make no, even free system, I guess. No, I mean, yeah, I don't know. Yeah, it's how the model changes is obvious, right?
Okay.
Whether you can do something for it, yeah, but this view of the system as a particle system, which is reflected with the reflection at 0, or maybe sometimes without reflection at 0, right? That's very, very generic. This has nothing to do with anything at all, right? So that's why I didn't like. So I said you can call it egalitarian trend or load balancing. And I don't like load balancing that much because load balancing is very narrow. Egalitarian trend can you can talk about it for free systems or something like this. Yeah, I'm not sure how. I mean, for what is done in this paper, this tightness that they stay close together is very important.
Okay.
I don't know. Maybe something can be. Maybe somehow we can get around it, but yeah, I don't know yet. but yeah, infinite number of extensions, and just like the previous question, yeah, if selection sets is increasing.
I didn't have a specific question. I just wanted to say hi. How are you doing, Sasha?
Oh yeah, hi.
I didn't really have a question.
Thanks for thanks for showing up.
Yeah. Are you well?
I'm okay. Yes.
Okay. Yeah.
Just.
Fine. Good.
Yeah, I have I have like a tons of relatives in Kiev right now. So
yeah,
so
well,
I'm calling them. It gives me daily dose of optimism. Quote unquote.
Yeah. Okay. Well, that's good. That's good. Yeah. You're getting some optimism at least. Yeah. Good.
Yeah. No, it's also okay. I was joking. It's usually not not very optimistic. Anyway.
Yeah. Anyway, well, yeah, fine. I'm going to have to head off, but it's great to see you, Sasha.
Okay. Yeah. Good to see you.
Yeah.
I'll see you.
Yeah. Take care.
I had another question. So, are there any systems, where we know that the IID property fails? Like
you mean uniqueness?
monotonic. Well, I guess what I mean is where the independence property fails. But I guess that follows.
Yeah. So yeah.
From the multiple fixed points. Yeah.
I see. So you're saying is there a counterexample when?
Right, because people are always making this conjecture, right? And we can prove it in certain cases.
Right.
But I guess I'm wondering, how far does that extend?
I don't know. It's quite possible that for specific system which I talked about, right? Maybe it's almost always true. So I didn't spend that much time, but yeah, I don't know counterexamples. But again, if you look at this model more generally, right, as some load distribution, right, then probably you can find some examples, right? So it's not necessarily cancel completion redundancy, but the system which has these two fundamental property, right? Egalitarian and monotonicity.
Right.
It may be possible to invent something when you get this weird situation when, for example,